Coble, and this is my Project 8 presentation for CE 570. Alright, so starting out, I wanted to outline the objectives for this project. Started out by assuming the composite body is the deformed body, define a symmetric Cauchy stress tensor field S, compute tractions on one of the surfaces, and then verify the total force on that surface. So below here you can see the symmetric Cauchy stress tensor field that I defined, and as you can see, based off the values, that it is indeed symmetric. This slide, it's basically going to outline how I plug each of the bodies into the Cauchy stress tensor field. So as you can see, here's body number 1, which is my hemisphere, and I plug that, and this is the new stress tensor field to represent that. And then my second body is my cylinder, and then I plug that into the stress tensor field. And then I also did that for my upright cone, and I got this stress tensor field. As you can see here, here are each of those outlined in my code. Here's body number 1, which is the hemisphere, body number 2, which is the cylinder, and body number 3, which is a cone. And they're pointing to each of those respective parts on my cone here. All right, so this slide is basically just outlining which surface we chose to verify. So as you can see, we chose to verify the outer surface of the cylinder, which is body part 2. And then on the right-hand side, this is just a quick snippet of my stress field for my MATLAB code. All right, so this slide is basically just outlining the traction calculations as well as the force calculations, and then verifying that that force calculation is identical to my MATLAB code. So starting out, I defined the normal vector, the outward normal vector, and then I multiplied that by the Cauchy stress tensor field, and I obtained the traction field right here. Then I integrated over theta and z, as well as multiplying by r, which is just dA. And then that's with respect to from 0 to 2 pi and 0 to h. And I defined r as just 8 and then h as 2. And then I had to integrate over E1, E2, and the E3 directions. So our E1 direction is 402.1238. E2 direction is 804.2478. And then finally, E3 direction is 2010.6193. And that is displayed in the bottom picture with the F vector, the force vector, and then finally that matches up with my MATLAB code. So it is verified. Alright, so here's a quick overview of my code. Most of these parts of the code are the same from past weeks, like the parameterization, the tangent vectors, the grid, the surface, the curve, the Jacobian, the area Jacobian. The main part that's different is the stress tensor field for each of my bodies. So first off, we have the stress tensor field for the hemisphere, body number 1, and then we have the stress tensor field for body number 2, which is my cylinder, and then finally the stress tensor field for body number 3, which is my upright cone. And then finally we have basically my generic stress field without any values plugged in. And yeah, so we'll run this here. It might take a little bit just because of the sheer volume of this. Alright, so as you can see here, I enhance the scale a little bit just so you can see the tensor field kind of popping out of the, so there's my stress field displayed, and then open up the command window here and you can see my values of the force on each of the surfaces, and then the total force on the and the surface area of my part.